So to take the derivative of log base 2 of natural log of x, this is y equals log base 2 of u, with u equal to natural log of x. So it's chain rule, which makes sense if it was on the chain rule homework assignment. To take the derivative of y with respect to u, dy du, that's the derivative of log base 2. So we have a rule for that. That's 1 over u times the natural log of the base. So 1 over u times the natural log of 2. And then we have a rule for finding du dx. If u is natural log of x, that's just 1 over x. And then those get multiplied together. So we end up with 1 over u, which was natural log of x, and then times the natural log of 2, and then times x. Does that make sense?
Yeah, thank you.
Sure. Any other questions from any of those assignments over break? We want to find the second derivative if we have the function or the equation xy plus x cubed minus y squared equals 1. So anytime you're asked to find the second derivative of an implicitly defined equation, first thing you have to do is find the first derivative. So take the derivative of both sides with respect to x. The derivative of x times y is a product rule. It's x times the derivative of y, which is dy dx, and then plus y times the derivative of x, which is just 1, and then plus the derivative of x cubed, and then the derivative of the minus y squared is minus 2y dy dx. Since we're doing it with respect to x, we attach the dy dx term to it anytime we take a derivative of something with a y in it. And then the derivative of the 1 is 0. And now we will solve for dy dx. So we'll keep y plus 3x squared on the left-hand side, and then we'll add over the 2y and then subtract over the x, and those are both multiplied by dy dx. So I can factor that out and get dy dx equals y plus 3x squared over 2y minus x. Everybody okay with the first derivative there?
Yeah.
All right, and so quite a few people that I saw for their second derivatives just tried to take the derivative of the top and the derivative of the bottom, but this is a quotient of two functions. So you have to treat it like a quotient. You have to use the quotient rule. So our second derivative, and it doesn't look like a y, needs to be done with the quotient rule. So it's the denominator times the derivative of the numerator, which is dy dx plus 6x, and then minus y plus 3x squared times the derivative of the denominator, which is 2 dy dx minus 1, all over that denominator, 2y minus x squared. And then all the dy dx's need to be replaced with y plus 3x squared over 2y minus x. So I'm not going to write that out, but you would just, rewrite it with the dy dx's as that dy dx. And I don't need you to simplify it any further than that. Just plugging those in is good enough. Good or no?
Good.
Anybody else have any other questions? All right, so to find the derivative of this one, this is y equals e to the u, with u equal to 4x minus 8 ln x. So we need to find dy du. And since dy du is just the derivative of e to the u, that's just e to the u. And then we have to find du dx, which ought to be the derivative of 4x minus 8 ln x, which is just 4 minus 8 times the derivative of natural log of x, which is 1 over x. So 8 times 1 over x is just 8 over x. And so when we multiply these together, we just get 4 minus 8 over x times e to the u, or 4x minus 8 ln x. Does that make sense?
Yes.
Yes. Cool. All right, next one was number 4 on the logarithmic differentiation one. So we had y equals tangent x raised to the power of e to the x. So whenever we're doing this logarithmic differentiation, we have to take the natural log of both sides. And that's whenever it's a function being raised to the power of a different function. So tangent x is a function, e to the x is a function. It's a function to the power of another function. So if we take the natural log of both sides, which allows us now, because we have something as an exponent within a logarithm, we can pull that exponent out to the front. So we end up with natural log of y equals e to the x times the natural log of tangent x. And then we'll take the derivative implicitly. So 1 over y dy dx equals the derivative of this, which is e to the x times the derivative of natural log of tangent x. And that's natural log of u, so 1 over u, times the derivative of tangent x, which is secant squared x. And then plus natural log of tangent x times the derivative of e to the x, which is e to the x. So far good with that one or no?
I'm just confused about the secant squared x.
So natural log of tangent x, this is natural log of u with u equal to tangent. So the derivative is 1 over u times the derivative of u, tangent x, and times the derivative of tangent. Derivative of tangent is secant squared. So it's secant squared x over u, or secant squared x over tangent x. And that's the chain rule on the derivative natural log of tangent x. Does that make sense or no?
Yeah, thank you.
All right, so now try and simplify it as much as we can here, and also we need to multiply by y. So we got dy dx equals y times all of this, which is e to the x, and then secant squared over tangent is 1 over cosine squared over sine over cosine. So I can, first off, I can cancel this cosine with one of the cosines. And so now I've got 1 over cosine divided by sine, which is just a sine and a cosine in the denominator. So e to the x over sine x cosine x. Or if you wanted, you could make it e to the x cosecant x secant x. That'd be fine too. And then plus e to the x times natural log tangent x. And all we have to do now is turn that back into its original function. So y was tangent x to the e to the x of tangent x to the power of e to the x times e to the x over sine x cosine x plus e to the x natural log tangent x. Good or no? Any questions or issues on that one? Any other questions on anything else from any of those assignments? Number 16 on chain rule number 2. All right. So let me pull back up the chain rule sign real quick. Inverse secant of sine x, right? So inverse secant of sine x. So to take the derivative of this, this is the chain rule. It's a function sine x or u within another function, inverse secant x. So inverse secant of u with u equal to sine x. The derivative of inverse secant of u ought to be 1 over the absolute value of u times the square root of u squared minus 1. And then we got to multiply that by the derivative of sine x, which is cosine x. So we get cosine x over absolute value sine x square root sine squared x minus 1. Good or no? Yep, you can just leave the absolute value like that. Absolute value sine x is just absolute value sine x. Yeah, since sine is sometimes positive and sometimes negative, you can't clear it out. Just leave it as is. Any other questions, anybody, on any of those assignments? Or anything just in general about what we've done in the last 3 weeks before Thanksgiving? So I've already written it up here. This is a rule for finding the derivatives of a inverse of another function. So not just specifically inverse trig functions that we're worrying about now, but just anytime we have a function that is an inverse of another function, we can apply this formula to find the derivative. So we're going to go through and sort of explain a little bit about why this works. But the inverse of f, its derivative at some point a, is equal to the inverse, right, the reciprocal, 1 over the derivative of the original function at that b value. So before we get into sort of why this works, let's think about what we know about inverse functions. For example, if, let's say we have a function that has the point 2, 3 on it. What could you tell me about the inverse function? So let's say f has the point 2, 3. What can you tell me about f inverse?
It has the point 3, 2.
It must have the point 3, 2, right? That's a hard and fast rule for inverse functions, is that take any point on the original function, flip the x and y coordinates, and it's a point on the inverse function. And why is that the case? Well, that's because it's always a reflection over the line y equals x. So we can exchange the x and the y values on the point because we're reflecting it over the line y equals x, right? It's always a reflection over that. What's something else we know about inverse functions? What is f composed of f inverse?
X.
Yeah, it equals x. And what is f inverse of f of x?
X.
Always also x, right? So there's a lot of these little sort of similar little relationships here, that the composition of a function its inverse is always x. That's because it's a reflection over the line, y equals x. And same as the inverse function composed of the original function is also x for the same reason. And we have that same relationship where we just flip those points. And so that's why this ends up working, because if I take any point, any point whatsoever on this function, let's say the point a, b, right? Well, that means that the other function, the inverse of it, has the point b comma a. And well, that's, that's how we find these slopes, right? Is this rise over the run. And if we're going from an a, b to a b, a, just, supposing we started at this point right here that was our y-intercept and then went to AB, right? That slope would be the inverse of the slope from the x-intercept here to the point BA. And no matter what point we choose, whether it's some point, on the function to compare to AB, or if it's some point exceptionally close to A comma B, where we're looking at really a tangent line, right, where we're doing the limit as h approaches 0 of it to find the derivative, to find the slope of the tangent line, that fact that these are inverses is still going to hold up. And so we can always say that if two functions are inverses, then at this point that is related, that they don't share the point, but they sort of share the point, we know the slopes are inverses. So sometimes I found it's helpful for people if I kind of write it out this way. If f and I'm going to call it g, if f and g are inverses, and f contains the point a, b, then we know g contains the point to what? B comma a. And f prime of a is equal to 1 over f prime of b. Or not f prime, g prime. That was the whole point of this. Okay, so if these are inverse functions, the derivative of one of them at its x value is the inverse of the derivative of the other one at its x value. Good or no?
Good.
All right, let's see if we can do this. We're going to do it with a function that we could find the inverse of really easily. So we're going to do it using the inverse rule, and then we're going to actually find the inverse and prove that we've done it correctly. So we want to find g prime of 8. So the first thing we're going to do to find g prime of 8 is think about what that means about the function g. It means that the function g contains some point where the x value is 8, doesn't it? That's not all that tells you. And if we're looking for g prime of 8, that g better have a point where x is 8.
Yes.
Yeah. So since g and f are inverses, what does that tell you about f? It must have a point where the
Y value is 8.
Where the y value is 8, exactly. And if we are looking for g prime of 8, it ought to equal 1 over f prime of whatever that value that should be the x value when y is 8 is. We just need to figure out what that value is, right? Everybody agrees that this is what that rule says?
Yes.
Okay. So how do we figure out when f of x has a y value of 8? Well, set f of x equal to 8, right? So x cubed equals 8 when x is
2.
2. So this point is 2 comma 8. This point was 8 comma 2. And g prime of 8 ought to be 1 over f prime of 2. So first off, what's f prime of x?
One over g prime of y.
Well, yeah, but just in general, what's f prime? We need to find f prime of 2, right? So in order to figure that out, we need to know what is the derivative of f. What's the derivative of f?
3x squared.
3x squared, right? Which tells us that f prime of 2 is 3 times 2 squared, or 12. So f prime of 2 is 12. So g prime of 8 must be 1 over 12. Good or no?
Good.
All right, cool. So let's just for fun, if f of x was x cubed, how do we figure out what the inverse function of that is? We'd rewrite this as y equals x cubed, and then what would we do?
Solve for x.
Okay, solve for x and then exchange the values, right? Normally I exchange the values first, but that's fine. We can solve for x. This gives us the cube root of y is equal to x. And so to find the inverse function, we just flip the variables and get y equals the cube root of x. Right, so f inverse of x, which is g of x, is x to the 1/3 power. And what's the derivative of that? What's g prime of x? That should be 1/3 x to the negative 2/3. Everybody agree with that?
Yes.
And we were looking for g prime of 8. So if we go back in here, g prime of 8 is 1 over 3 times 8 to the 2/3 power in the denominator. And a 2/3 power on 8 makes the 8 turn into a 2, and then square the 2 to get a 4. So this is 1 over 3 times 4, or 1/12. And we can see that by actually going through and finding the inverse, we get the same exact value as we did by just using the inverse rule. So this inverse rule is super convenient. One, when maybe finding the inverse of this is kind of a pain, or might give you something where the derivative of the inverse of it is really annoying to find, but the derivative of f is easy to find. And then the other option of why this would be important is when you're given a function like this, where f of x equals e to the x plus x, and there's no good way for you to explicitly define the inverse function of f. And if we tried to do that same thing that we did to solve for x, how are you going to solve y equals e to the x plus x for x? Right? That's not gonna work out very well. You're not going to be able to solve for x. So we have to use this inverse rule. So we're given that f and g are inverses, and we want g prime of 1. So if we want g prime of 1, that tells us that g must have a point that is what?
Has an x value of 1.
has an x value of 1 comma something, which tells you what about f. F must have a point that is related to that point where the
And the y value is 1.
y value is 1. So in order to figure out what that is, we need to figure out when does e to the x plus x, when does f of x equal 1. Anybody see a value of x that makes that true?
0.
Yep. Looks like that's true. There's not like a nice easy way to solve it, but if you just think of some numbers, like plug in 0 for x, e to the 0 is 1, plus 0 is 1. So perfect. That makes the points 1, 0, and 0, 1. And if we want g prime of 1, it ought to be equal to 1 over f prime of
0.
0. And what is f prime of x?
E to the x plus 1.
Ought to be just e to the x plus 1. And so if we want to find f prime of 0, that's e to the 0 plus 1, which is e to the 0 is 1, right? Plus 1 is 2. So this gives us 1 over 2. Good or no? Any questions, any issues there?